Here's another video on section 5.8, modeling with variation. These are the typical homework problems that they have in the book. Like number 26, when y varies directly as the cube of x, when x equals 3, y equals 5, find y when x equals 4. What that means is when y varies directly as the cube of x, that just is the language that they're using to describe the fact that y is equal to some constant times x cubed. It varies directly as the cube of x. So then they give you 2 points, there are 2 values, x equals 3 and y equals 5, that let you solve for k. And when you solve for k, you can plug that in and actually have a formula for y in terms of x. And then you can answer, they ask you to plug in x equals 4 and you get some answer down here. Similarly, you could have number 32, where y varies inversely with the square root of x. So what that means is y is proportional to, if it's inversely, it's divided by some power of x. And in this case, they say it's the square root of x. So inversely means they go opposite. So x is in the denominator. As x gets bigger, y gets smaller. So they go opposite. And it's the rate at which it gets smaller is the square root of x. So here they give you x equals 64, y equals 12. So you can plug that in and solve for k. So 12 equals k over 8. 96 equals k. So you have your formula, 96 over the square root of x. That's your formula. And then they tell you to plug in some value. So let's say plug in x equals 36 is what they say. And so you can simplify that, 96 over 6, which is 16. And so they give you these formulas in the book that say the variables are related in this way. Y varies with respect to the square root of x or something like that. And then you can just find the constant that goes into that equation. But it turns out, so this has a lot of practical uses too, where you can just understand the relationships between 2 variables. For instance, suppose I'm going for a drive. How are my speed and the time it takes for me to drive related? Well, we know an equation. Distance is rate times time. So the rate varies inversely with the time it takes. My speed, or my rate, varies inversely with respect to the time. If I go faster, it takes less time. They go opposite. And the formula is just the constant equals the rate times the time. And so if you solve for one of the variables in terms of the other, like in terms of time, the rate is d over time. And so that is going to give you an expression similar to y equals k over x, with minutes, time as the input, and rate or speed or miles per hour being the output. You're going to get a 1 over x type of equation. So as your minutes takes longer, your miles per hour is less. Conversely, you can solve for, in terms of the rate, you can find the time. And so that's also going to be plug in miles per hour, and your y value, your output, is minutes, and it's again going to be a 1 over x sort of expression, an inverse relationship. And the function will look like that. So how can you solve some of those things if you have examples? So let's say I increase my speed from 50 miles an hour to 100 miles an hour. How does that change the time that it's going to take? How are those related? Well, I can't solve this exactly for how many minutes I'm going to save because I don't know the total length of the trip, but I don't need to know. So I don't need to know that constant to answer some questions. So look at it this way. If I double my speed, instead of x miles an hour, I go 2x miles an hour. How does that change my time? Well, I can factor out that 2 in the denominator, that 1/2, and d over x is just my original slow time. So if I double my speed, my time is cut in half. And that proportion goes the same way. If I triple my speed, if I increase it by a factor of 3, then my time is 1/3 of the original time. And you can use that relationship in lots of ways. So let's try it with different numbers here. So let's say I go from 50 miles an hour to 60 miles an hour. So I'm not doubling, but I'm increasing by some fraction. I can plug that fraction into my formula here. And instead of going x miles an hour, say I go 6/5 times x. So that would change me from 50 to 60, or it can change me from x to some larger value. How does my time change? My time goes by the opposite fraction, the reciprocal. And so my time will decrease to 5/6 of what it was. So that's 1/6 slower. So that's 16% slower. So if I go 20% faster, I know I'm going to take less time, but it's not 20% less time. It's only 16% less time because it's this reciprocal relationship. If I go 6/5 times my original speed, my time is 5/6 of my original time. And that's an inverse relationship. Let's try a different example with, here we've got two trophies. First place trophy is 10 inches tall, second place trophy is only 6 inches tall. If they're scaled, there's a couple ways that we can think about relationships. How is the width related to the height? Well, the width varies with the height. So what I mean is the width is equal to some constant times the height. They scale together. And so if I have, if I change the height, so the width is k times, let's say I change the height and I scale it up by 10/6. That's my scaling factor. Right? It's 10/6 times as tall as the shorter trophy. So then what happens to my, my new width is equal to, I can factor that 10/6 out and get kh here, which is 10/6 the previous width, the small width. So in this case, I know my small width was 3, and so I get 5 inches wide, the new width. But the point is, this 10/6 can factor out. If I increase the width by 10/6, then I increase the height by 10/6, then I increase the width by 10/6. They're proportional, right? So what happens in different cases? So let's try those same two trophies, but now I want to know how much liquid goes into those trophies. What's the volume of that trophy, right? This one says the small one holds 1 liter. So how much does the big one hold? Does it hold 10/6 of a liter? Do I scale it by 10/6? No. In this case, we're talking 3-dimensional. Volume is a 3-dimensional thing. I don't know a formula for the volume of this trophy, how much liquid it can hold, but I know it's 3-dimensional. So I know it's probably taller, it's probably wider, and it's probably deeper. So it's scaled in 3 dimensions. So I don't need to know an exact formula for this, but I know the volume varies with the cube of the height. It might not, it might not be exact, but in general, that's how volumes translate. So let's assume that trophy expands the same direction in all 3 dimensions. Then the volume will expand by the cube. And so I can have the volume is some constant times the height. I don't know what that constant is, but I don't need to know. If I have the original height in here and I scale it by 10/6, that's the scale again, then I can factor that 10/6 out, but it becomes 10/6 cubed times kh cubed, right? So that's 10/6 cubed times the small volume. So the big volume is scaled, but it's scaled by 10/6 cubed, right? So whatever that calculation is. So if the height were to double, then the big volume would be doubled cubed. So 2 to the 3rd, which is 8. So if I doubled the height, doubled the width, double the volume, or double the length, then I will cubed the volume. So let's suppose that the first place trophy takes 4 ounces of gold paint to paint it, right? The bigger one takes 4 ounces. It's not real gold, it's gold plated. So let's say it takes 4 ounces. We're talking about the surface area of the trophy. So what's the area of the trophy? Well, the area is a two-dimensional thing. So it's going to be squared as the square of the height. Two-dimensional things will double. So this will be twice as tall, but it'll also have twice the circumference, right? The radius will be twice, so it'll have twice the circumference. If it's doubled in 2 dimensions, it's going to be squared as the height. It's various square of the height. So what we can do then is, let's say, what's the scaling factor going from the big to the small? That scaling factor is 6/10. So the scaling factor in this case is 6/10. The big one is the standard, and now we're going down to 6/10 of the height. So how does the area change? Well, the area then, the small area, is 6/10 squared times kh squared. So it's going to be 6/10 of the big surface area. And so you can do these scaling factors up to the big or down to the small, but keep in mind what the dimension of what you're using is, and that often, at least in a general sense, we don't know an exact formula for this trophy, but generally it's going to doubling the height will increase the area by 2 squared, and it'll increase the volume by 2 cubed. And so you can use that scaling idea in lots of ways to answer some questions.